Hello my dear 11th moving 12th standard students. One of the most important chapter and very simple easy peasy lemon squeezy chapter of 11th standard, and that is solid mechanics and elasticity. Will guaranteedly fetch you 4 marks next year in your JEE 2025 examination. So let's conquer this chapter. Let's get to know what is there in this chapter, and also remember that there are certain concepts in this chapter which is used in fluids, also in sound waves, and sometimes even in some other chapters, like suddenly they give a mixed question, maybe in Newton's laws on or in rotational motion. So even in thermal physics you will see the concept of elasticity being used in 1 or 2 problems here and there. So let's get this chapter done and make sure that we learn right from the basics to the advanced level, so that we can solve all kinds of questions. And if this chapter is a backlog for all of you, this session is going to be very fruitful. And start marking your attendance right away right now. Hello Kana, hello J24 gift, welcome Sakti, hello Shri, can I get 99 percentile from starting from now? Yes, definitely. And make sure you start attending all the classes that we are making for all of you for the second attempt for JEE 2025. For JEE Advanced, everything is going to be done on this channel. So it's a time to rebound, and I will give you a separate plan on how to rebound for the second attempt as well. Alright, so let's begin with the lecture. And those of you who do not know me, well, my name is Shreyas. People call me also Captain Shreyas, and I have been teaching for more than 11 years now. And over this period of time, I am very happy and very delighted that students have made me proud by entering IITs, and I'm so happy about this fact that I was able to guide and mentor below average students and help them achieve their potential, because many students feel that they lack the capability or that intelligence, or I don't know, the things which are needed to actually enter IIT. But it is not so. Even a below average student can actually enter into the dream college, into the top-notch colleges in the country. All you need is a particular very good mentor, you need good content, you need a systematic schedule, and obviously you need that inner motivation and that self-discipline. If you have all these parameters together, nobody can stop you from entering your dream college, right? So let's begin with the lecture. All right, I hope you have smashed the like button. Hello Kodeti, hello Atheria. Sir, physics board exam was tough, I know. Yes, it was tough for most of the students, I know that. Don't worry, it was tough for everyone. So I hope they do something good about it. Okay, so let's concentrate on the next things at hand. Don't worry about what has happened before. Don't worry about what has happened in the past, or what is bothering you right now. Just put it aside. Look forward for the next attempt, look forward for the next exam, look forward for the next year. That is what the mindset should be. Hello Yujita, nice to see you live for the first time too. Puriti Kumari, nice to see you too. I hope you guys have marked your attendance. So let's begin with the lecture. Starting off with rigid body, solids, elasticity, all these topics are more or less connected to each other. So first let's understand what is the meaning of a rigid body, elastic body and plastic body, because that is what this chapter is going to start off with. So there are 3 kinds of bodies that we are going to talk about. One is your rigid body, then comes your elastic body, then comes your elastic body, and the last one is your plastic body. There are 3 kinds of bodies which are there in nature, and in this particular chapter we are going to study elastic bodies. I will tell you about rigid and plastic bodies because that is there in the theory part. So to start off with, what the meaning of the word rigid? Rigid means does not change, does not get affected. That the teacher is very rigid, meaning no matter what you tell, ma'am please give a break, teacher will not listen. Ma'am please leave us here, or can I come after 5 minutes to the class, I will be late. No, teacher won't listen. So that is rigid. You don't get affected, you don't change for anything. Is that right, everyone? So rigid body means a body which doesn't which doesn't deform. It doesn't deform due to external forces. Due to external forces. That is the meaning of rigid body. You might think of diamond or a heavy rock as an example where you apply huge force, but still there is hardly any changes in the shape or size. But you apply a force on your friend, his cheek will get deformed. Or you apply a force on a plant, the plant will bend. It is not a rigid body. Correct? You apply a force on clay, chewing gum, pizza, right? All these things, you can easily bend them. You have a scale, you can bend it. It is not rigid. But a very, very thick iron bar, it's almost not going to bend. It's not going to change its shape. It's very difficult to change its shape and size. So that is a rigid body. The other end of this is a plastic body, meaning you apply a force, it deforms and it doesn't even make an attempt to come back to its original shape. It permanently deforms itself. Not just that, it is so flexible that once you bend it, once you deform it, it stays there as it is. So they undergo permanent deformation. They undergo permanent deformation, and don't restore, and they don't restore their shape or their size. What is a good example of a plastic body? Have you seen how chapati is made? Have you seen how pots are made with clay? The chapati is made with dough, right? The dough that you use, you mix the wheat and the water and all those things, and then you get the dough. It's plastic. You push it, it bends, it gets a nice shape and it stays there. Even clay is used to make pots. You press the clay, you pull the clay, it will get deformed and it will stay there as it is. So that is also plastic. A chewing gum or cheese, you pull it, leave it, it stays, it gets elongated and it stays as it is. Is that right? Yes, the permanent deformation. Yes, Sri Ganeshan. Perfect. Yeah, Yujita, you can watch it even if you are a 12th passing out student, but yeah, we have designed this class specifically for 11th to 12th moving students, so we are going right from scratch till a very good level. So that is a plastic body. Elastic means they get deformed, but that is temporarily. That is just temporary deformation. It's not permanent. It's temporary deformation, and they get back to initial shape and size, both initial shape and size both. Like for example, I can tell you this particular scale that I have is an elastic scale. How do I know that? I bend it, I leave it, it comes back. Everybody is able to see this particular scale? Everybody is able to see this particular scale? So I take this scale, I bend it, I leave it, it's deformed, but it is temporary because when I leave it, it comes back. You might have seen rubber band. You stretch it, it gets deformed. It is elastic in nature. You release it, it comes back to its original shape and size. Understood the difference between these three? Yeah. Yes, Cosmic Art, you can ask the doubt. Yes, Yashwant, you can watch it. Yes, Sudeshna, 18, glad. Okay. So if these three distinguishing factors are very clear in your head with examples in your head, please give me a thumbs up, smash the like button or put it up in the chat box if you have already done it. Yeah, so elastic body, I can put examples over here. Example of rubber band. Example of a rubber band. That will be a very good example. If you talk about plastic body, the example will be of clay or duff. Right. Then if you talk about the example of rigid body, actually speaking, no such body is rigid in nature, but you can approximately say that a stone is very rigid, or let's say diamond. Diamond is very rigid. It hardly deforms when you apply any forces. No such body is perfectly rigid. No such body is perfectly plastic, because there will be some kind of variation, some kind of small, deformation which might happen at very, very small level or atomic level. So no such thing is perfectly ideal. Remember that. Great. Yeah. Rubber band. Yes, rubber band also. Spring, scale. Yeah, so many examples. Correct. Now we are going to particularly focus on elastic bodies. We are going to particularly focus on elastic bodies. Elastic bodies. Say for example, you might have seen your eraser, your rubber, right, which you use in schools. Sometimes people love to smell that rubber also. It smells also very nice, especially that new rubber. How many of you like that smell? I used to like it a lot. And also when you cut it also, it looks very fancy, especially if it has multiple colors in it. So the erasers or those rubbers which you have been using at a lower grade, maybe, if you take an example, let's say this is our rubber. This is our rubber like this, or eraser. If you look at it at a molecular level, at a very, very deep level, you zoom onto it, you will see it is made up of many, many atoms and molecules, right? It is made up of many, many atoms and molecules. Perfect. So something like this. In fact, there will be many, many, countless, it's like crazy, lots of particles, or I can say molecules, lots of molecules it is made up of. Now when you zoom onto it and then see how these molecules look like, you might see one molecule of rubber here, another 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 molecule here, another molecule here, something like this. So there is empty space between them. These are nothing but, what are these? These are nothing but molecules. These are nothing but molecules of rubber. What you will see is a very interesting thing, and that is the empty space between them acts like a spring, meaning when somebody tries to press this rubber, pulls this rubber, twists this rubber, you will see these molecules will go away, will come close or go in different directions, but there is some intermolecular forces between them. And how is this intermolecular forces? Well, their behavior is like a Pandu-Champa relationship. Imagine this is our Pandu. And this is our beautiful Champa. They maintain a certain separation between them. Let's say that is 1 meter. Example. Now, what happens? Pandu gets very attracted to Champa. So Pandu comes very, very close to Champa. Alright, Pandu comes very close to Champa. And Champa is also attracted, let's say, to Pandu. But then they realize, no, we should not come so close. It is not good for us. So what happens is, they will repel each other. They will basically repel each other. If they try to come close, they'll be like, no, we should stay away from each other. It is not good for our relationship. Then what happens is, another day, Pandu gets mad at Champa. They have a fight. So Pandu and Champa go really, really far away from each other. They fight with each other or something. Then they realize how much they love each other. So Pandu then gets pulled, gets attracted towards Champa. So when they go far, they come close. When they come very close, they get repelled and they try to push themselves away. There is a certain distance at which they stay at equilibrium. And this is true not just for Pandu Champa, but also for all the atoms and the molecules inside a solid. Yes, it is also true for atoms and molecules inside a solid. They can't come so close, they can't go very far away. They want to maintain a certain distance. So when you try to push something, this will happen. The molecules will come close, they will try to push themselves away. When you try to pull a solid, what happens is the molecules tend to go away, and then there is a force which is trying to restore them back to their original position. Are you getting a feeling? Are you getting a sensation? So is it not like as if there is a spring between them? As if there is a spring between them. Here the spring is elongated, here the spring is compressed, and here the spring is at its natural length, That sensation you are getting, it feels as if it is extended, Here it feels as if it is compressed. Isn't that right? So this is what exactly the molecules of a solid also feel like. They feel the spring-like forces between them. So you can think of imaginary springs. There are no actual springs. So please do not think that, inside a solid there are springs. No. These are just imaginary springs which I am drawing so that you get the understanding of how the behavior is. Okay, so this is how it looks like. I'm just showing some random springs here just to show you get you a feel of the situation. See, this is how it looks like. Isn't it crazy? This is how a solid looks like. These are just imaginary springs. So the molecules of a solid show or behave as if there is an imaginary spring between them. So that is why this elastic property comes into play. Because whenever you pull something, it tries to come back. Whenever you push something, it tries to again go back to its original shape. That is the reason why an elastic body gets deformed temporarily and it tries to come back to its original shape as well as size when you release the force. Example, rubber band and so many other, steel scale, bending it comes back. So this is what is happening at molecular level. Okay, I hope this is very, very clear. So when we talk about any elastic body, let's say it is like this, then I pull it, I stretch it or something like that. Okay, so right now this particular body, let's say, is at its natural shape and size. Let's say now I have basically deformed this particular body. by pulling it or something. So let's say I have pulled it and I have applied some force from here. So this force which I will apply from outside is that external force, is the external deforming force, But at the same time, because the molecules of this solid want to come back to its original shape and size, what you will also see, the spring-like forces will try to bring it back to its original shape and size. So there is simultaneous restoring force. And when the body is neither extending nor contracting, it's maintaining its new shape, its new size, this and this will be both equal in amounts. So if the body has already been extended, the body has already been compressed, the body is already being twisted, it's no longer moving, it's in equilibrium, there is no motion, so the deforming and the restoring forces will be equal. So the restoring forces are all going to be because of the spring-like forces, so this is due to the spring-like forces. Another good example of this is probably your actual spring as well. So this is your actual spring. Right now it is in its natural state. I pull it and I see it gets extended. By an amount of X. And this happens due to an external force which is trying to deform it, and the spring will experience a restoring force Fs like this. And we know this Fs, will be equal to K into X, K into X. What is K? K is basically called as your spring constant. Spring constant. These are all magnitudes. Don't think about the minus sign. Many people will think, sir, where did the minus sign go, sir? No, I'm just talking about the magnitudes. So it's a positive value which is equal to positive into positive value. So spring force will be some constant of that spring, which is called as the Spring's constant, which is often expressed in newtons per meter. How much Newton force you need to extend it by meter. That is the spring constant. And this spring constant force will also be equal to the external force. The external force. Is this very, very clear in your head? Yep. Mighty will be launching the new round 2 series for all of you just after the maths exam. Don't worry about it. Yep. Perfecto. Perfecto. Awesome. Awesome. Let's now move ahead. So we have talked about how an elastic body behaves, how there are imaginary springs between the molecules of the solid. We have spoken how an equilibrium distance is maintained and why a restoring attractive or repelling force comes into play. And we have also talked about how these two forces of deformation and restoration are equal once the body has been extended. Okay, great. Now that you understand what happens overall, you have an overall picture of what happens at the molecular level. Now let's actually come to the main part of the chapter where we talk about 3 major types of deformation. Then there is a graph and some energy related calculation, and then we can go to the problems part. So in this chapter, we study mainly 3 major types of deformation. Any other shape and any other combination of deformation we do not study for the JEE level. We do not study till the 12th standard. If you take aeronautical engineering, or if you take mechanical engineering, or even if you take metallurgy, or even if you take any such branch of engineering which involves some solids, some structures, like even civil, there you will be studying some complex behavior of deformation. If you think about it, even your building is not perfectly rigid. You might say, sir, this wall, sir, I hit it, it doesn't move. But during an earthquake, you can see the building shake. So there is some amount of flexibility. Your vehicle is also not perfectly rigid. It bends. If some vehicle hits your vehicle, you can see a dent in the vehicle. Even heavy rods are not perfectly rigid. They can be bent, but you need a heavy force. Maybe if you hang an elephant onto it, maybe it will bend. Or maybe you can, compress or elongate it. Definitely it is possible. And these play a very, very vital role for all your designs. Like for example, when you design a vehicle, you ensure that the front part is made of very tough material or very soft material or very brittle material or very plastic material or very elastic material. That is the question in front of you. Let's say you are the designer and you have to design the front bumper, the front part of the vehicle. How will you design it to be? Yes, Ansar Ali. How will you design it to be? Will it be very rigid? Will it be very ductile, malleable, that kind of soft? Or will it be brittle, meaning it breaks into pieces? Or do you think it will be plastic, that means ductile and malleable? What do you think? How will it be? Or will it be elastic, that means it absorbs the shock and comes back to its original shape and size? What do you think it should be? Yes, even Einstein thought that space is elastic in nature. So my dear friends, it so happens that the front part of your car is designed to be very brittle in nature, because whenever something collides with your car, let's say it is rigid, it does not break, it does not bend, it does not deform, then all the energy of the collision is transmitted throughout the car, including the passengers. Imagine the amount of energy which is there in the collision and all the passengers getting that shock. It will be very, very injurious. So you cannot make it very rigid. How about making it, elastic? Let's say it gets deformed and comes back to the original shape. So guys, the vehicles collide. Okay, they deform and they come back to their original shape and size, and the vehicles are thrown apart again. That would be very funny to watch. So that also does not happen. So it is not elastic. So is it plastic or is it brittle? It's a combination of both actually. So some parts are designed to actually bend. So if you think, oh, this car, how did it bend? It was designed to bend so that it can absorb that shock. Some parts are made brittle so that it can actually break the bonds, absorb that energy, and that energy is being absorbed to break the bonds and to break it into small pieces, so that the energy during the collision is not going to the passengers but is actually gone into those small pieces. So that's how, you know, the parts are designed. So this plays a very important role, not just here, even in rockets, even in your normal buildings, even while designing your normal table, your computer, your phone. Your phone is also involving so much of, you know, material behavior, like, oh, the glass should be, you know, elastic, it should be able to bend little bit, because when you keep the phone in the pocket, the you know, legs might bend, the phone might bend, it should be able to bear that strength, right? If it drops, then you know, it should not break. This part should be sturdy, this part should be flexible. So there is a lot of material science, solid behavior analysis which goes into your day-to-day objects. Understood, my dear warriors? Okay, great. Let's now go to the three major types of deformations and their formulas. Now the three major types of deformations that we are going to study. So the different types of deformations, that we are going to study. Number one, we are going to study is longitudinal. Number two, we are going to study shear deformation. Number three, we are going to study is bulk deformation. Now usually these two, longitudinal and shear, we use it mainly for solids. This bulk deformation is mainly used for liquids or gases. Liquids or basically gases. This is where you use this particular deformation for. What do I mean by longitudinal deformation, shear deformation and bulk deformation? Let me show it to you on the next slide coming up on your screen. See, it so happens that if you talk about longitudinal deformation, what it means is that you take a rod and you pull it from both sides. Okay, so what happens? The rod might get elongated. So you have basically applied a force like this. You have pulled the rod. So the extension or the change in the length is happening along the direction of the force. The change of length is happening. So the change of length is happening along the direction of the force. Such a deformation is called as longitudinal deformation. This is called as a longitudinal deformation. Is this clear? The force and the change of length is parallel to each other. The force and the change of length are basically how they are parallel to each other. Very good. Next is your shear deformation. Imagine there is another rod or box or solid like this. Okay, and what you do is you apply a force parallel to the surface, not perpendicular to the surface. See, this was the surface, you applied perpendicular in this particular situation. The force was perpendicular to the surface and the force caused the change, you know, along the same lines. But this time the force is parallel to the surface, and what you see is this particular solid will bend like this. Something like this. Think of it this way. It has bent. Are you able to visualize? You apply the force parallel, the solid will bend like this. So you can see the deformation is happening here. So the changes are again happening here, but this time the force is parallel to the surface, which is which is changing its relative position. Earlier this surface was here, now this surface has slided over here. So there is sliding motion happening. This kind of behavior is also called as shear behavior, and the deformation is called as shear deformation. This is called as shear deformation. You can take examples of many things, like for example, I take this particular book. I have this book. I have this particular book. I move this book like this. You will see that is shear deformation. That is basically shear deformation. I am applying the force like this, and you can see all the pages are moving parallel to each other, and you can see the whole object has bent. The whole object has basically bent. Yep. Where can we use shear deformation? There are many examples of both of them. I'll give you one each, don't worry. So say for example, in this case, you take a wire and you hang something. You take a wire and you hang something. What will happen? This material, which is making up the rod or the thread, will elongate slightly, because the mass of this box will pull it down. So definitely there is longitudinal deformation. So this mass has pulled this rod, right? So that is longitudinal deformation. Sometimes it might happen that there is a rod which is over here, and then there are two surfaces. Maybe it is jammed between them, maybe it is stuck between these two surfaces, and then what happens is somebody pushes these two surfaces together. So this will begin to crumple, this will begin to compress. So this is also longitudinal deformation at the end of the day, because the force is perpendicular to the surface. The force is perpendicular to the surface, and the forces are causing the deformation along the same line. So that is a longitudinal deformation. Example of a shear deformation could be, imagine you take a rod like this. You take a rod like this and you apply a force here. You hang some mass over here. So what will happen is that you will see that this rod will bend like this. This rod will bend like this. So what has happened? Each layer has slid before the previous layer. There is sliding which is happening, and the forces are parallel to the surface. The forces are parallel to the surface and there is sliding happening. So this involves shear deformation. Is that clear? Yep. Everybody with me? So another example I just told you about is having multiple pages of a book. Multiple pages of a book like this. Okay, it might be in this particular shape. So after you apply the force, one page is here, one page is here, one page is here, another page is here, another page is here, another page is here, another page is here. So there is shear deformation which is happening because you applied the force in this particular manner. You can see it has been bent. Understood? So these are some examples of shear deformation. Even when vehicles go on the road, the tar, the cement experiences not just longitudinal but also shear, because the wheels try to rotate and push the surface behind. They try to push the surface behind. Imagine this is a block of cement or tar. So the vehicle is going like this. The tire will push the upper surface behind and the bottom surface is being held by the ground. So you will see there is shear forces involved, shear deformation involved even on a normal road. Okay, because the one part of the road tries to slide with respect to the other. So whenever there is sliding which is happening of one layer with respect to the other, that is basically shear. Is it now clear in your head, my dear warriors? Yep. Very nice. What is the next type of deformation? What is the next type of deformation that you have? The next type of deformation that you have is bulk. Where imagine you have a gas or a liquid, and you heat it, or you you compress it, or basically release the pressure. Basically some variation in the pressure happens, and then you see that the gas or that liquid expands or compresses. Either it expands or it compresses because of changes in pressure. So this was a liquid or this was a gas. So suddenly the pressure was changed, so because of which it expanded, let's say. So that behavior is called as bulk deformation, bulk behavior. Bulk deformation or bulk behavior. So bulk means complete. Bulk. I took all these apparatus in bulk. I took all these materials in bulk. Bulk means in a big quantity, as a whole, as a complete. We ordered everything in bulk, means together. We did not spare anything, as a big quantity. That is what the meaning of bulk is. So if you take a balloon, right, and let's say the outside pressure increases, what will happen? The balloon will shrink. So bulk deformation. Same way, if you go deep inside water, the pressure is very large. So what will that pressure do? That pressure will compress. That pressure will compress the liquid inside. And you will see the density of the water will change as you go deep and deep, because the forces are so huge, the water molecules will try to come close, and because of which it will become more dense. So that is again bulk behavior. Is that okay? So that is why we use bulk behavior mainly for liquids and gases. Yes, great. Okay, now let's see the formulas. Let's see the main formulas which are going to come up. And before that, let me also remind you of one more thing, that our 11th to 12th moving batch is starting for all the JEE 2025 students, online and yes, offline as well. In fact, let me tell you that in online, we are going to have obviously live classes with the recordings and their notes being provided with the best teachers who have been producing ranks like All India rank 20, 28, 104, 59 and so on and so forth, with JEE Advanced and mains preparation and any other exam preparation that happens side by side, as well as board preparation also we help you towards the end of the syllabus, right? So remember, this also comes with tests, assignments, doubt solving, that to unlimited personal teacher, study material and anything that you would expect out of any coaching that is there, but you will also get things which are beyond, like unlimited doubt solving, personal teacher and the quality of the content without any errors, and the test series and the other exam preparation. That is something which you should look forward to. All right. So these are our strengths. These are our, unique points which make these courses for all the students very likable. And these students who have been with us are not just extremely happy, but have improved their marks like anything. And in fact, there is a special thing about Vedantu, like if you don't improve your marks, then we refund back the entire amount. So that is VIP, Vedantu Improvement Promise, which no other institute can guarantee. We are ourselves so confident that any student who joins our batches will guaranteedly improve. So obviously you can study from home, you have a good chance to save a lot of time and lot of energy, and that you can better utilize for studies. And obviously the courses are very, very affordable, priced at a very low point. So you can wait for this particular space where we are going to launch our 11th moving 12th batches, as well as the revision and the backlog batches as well in the days to come, so that you can cover up your 11th standard backlogs, you can cover up your 11th standard portions, and you can be ready for the JEE 2025 12th standard preparation as well. Also, if you are interested for offline batches, that link is also there in the description box of this particular video. So make sure as you are particularly watching this video, you fill up this particular form. You can see Vedantu online store is there, Vedantu Learning Center link is there. Just click on this link and you will be able to download the brochure, or you can schedule your visit to the nearest center. We are right now there in almost all the major cities across India. You can see all the cities are given over here. You can choose whichever city is close to you, and you can start attending the classes, make the inquiry, have an experience, get a free demo over there, see how the teachers are teaching, all the pictures, everything are given, all the facilities that you get, be it library, be it doubt counter, all these things are mentioned, okay? And you experience it. Don't just see it over here, experience it. You will be mind blown, trust me on this, okay? So that was a very important piece of information for all of you, because many students keep asking, sir, do you have an offline batch? Do you have an online batch? So yes, we have, and that too for 11th moving 12 kids. Link is there in the description. Make sure you fill it up. Okay, great. Now, let's move on to the formula part. Let's move on to the formula part. To go to the formula part, we need to define three quantities. One is stress, one is strain, third is modulus. of elasticity. After these three quantities, seeing those formulas will become very, very easy. So, first of all, let's talk about stress. Let's talk about stress. Stress is basically the intensity of the force which is there trying to restore it. The intensity of the restoring force which is present in a body which has been deformed or which is getting deformed. So I'll just mention over here, stress is the intensity of the restoring force in an elastic body which has been deformed, Meaning, imagine there is this particular solid and let's say you elongate it, something like this. So let's say there is a restoring force like this. There is a restoring force like this. This force is acting on this particular area. Can you see that? It is basically acting on this particular area. Let's say I call that area as A and this force as F. Intensity means how much force is concentrated per unit area. So that's all. If I divide that force by the area, what I get is the quantity called as stress. The symbol for that is sigma. The symbol for that is basically sigma. Sigma is force per unit area. Can you guess the unit of stress now? Can you guess the unit of stress? Force is in Newton, area is in meter square. So it will be Newton per meter square, or you can also call it Pascal. 1 Newton per meter square is nothing but Pascal. So that is the unit of stress. How much force is there per unit area? So think about it, my dear students. If I have a large area, first I'll take decent area, then I will take large area, and then I'll take the same area but will take different force. Imagine earlier this were the forces, now this is the force restoring, and then this is the force over here in a larger area. Here if the area is A, here also the area is A, here the area is more, Here if the force is F, here also the force is F, but here the force is more. Here if I call the stress is sigma, which is F by A, can you guess what will happen to the stress over here? Will it be higher or will it be lower? Because the same force is now applied on a large area, so the force which is there, distribution which is there, has been spread out on a larger area, so the intensity has reduced. So can I say sigma is less, the stress is less, because the force has been spread on a large area. Here the area is the same, but much larger force has been applied on that same area, so the concentration is more. So can I say sigma is basically more? Can I say the stress is basically higher? Everyone, can I say stress is equal to pressure? Siva, pressure and stress, although the formula looks same, but pressure we use it for liquids and gases. Stress we can use it not just for solids, but we can also use it for liquids. Okay, so although they sound similar, the usage, the application is slightly different. Okay, so generally we do not try to mix both of them. Okay, although they sound very, very similar, their applications are slightly different. I hope that is very clear. So now did you understand what is the meaning of stress? It is the intensity, how intense the force is, and it is the force per unit area. Unit is Pascal or Newton per meter square. That is your stress. The next quantity that we are going to talk about is the strain, is basically the strain. What is this strain? Strain is nothing but is the relative change in dimensions. Relative change in dimensions. Usually the symbol for strain is epsilon. And strain is usually how much is the change which is happening per unit original length or original height or original depth. So original length or original dimension which is there, and change which is there is in the numerator. If this is in meter, this is in meter. If this is in radian, this is in radian. If this is in centimeter, this is in centimeter. So the dimensions will cancel or the units will also cancel. So strictly speaking, epsilon is dimensionless. It is basically dimensionless and unitless. So there is no unit that you have for strain or epsilon. Okay, so keep this in mind. Just to give you an example of how to understand strain, imagine there was a rod whose length is 100 centimeter. Now the rod length, the new length became 101 centimeter. If I ask you to find the strain in it, what you need to do is the following. Strain is nothing but the change which happens upon the original one. Now how much is the change? From 100 it went to 101. So the change technically is 101 minus 100. How much was the original? Original was 100. So basically the strain is 1 by 100, or I can also call it to be 0.01. That is the strain. Is that very clear? Very good. Next important thing, you can also express percentage strain. Percentage strain is nothing but the strain multiplied by 100. That's it. That is percentage strain. So it will be 0.01 multiplied by 100. So in this case, it is 1% strain. Meaning 1% of the total length or the dimension will increase. If it was 1 kilometer, 1% of it would have changed. So that is how strain percentage can be understood. Usually you express strain as value like fraction or a decimal, but if it is given in percentage, that is also okay. But it is a dimensionless and unitless quantity. So do not get confused between strain, which is epsilon, and stress. Okay, don't get confused between them. Stress is sigma. S for sigma, stress, lot of S's are there, so sigma. That's how you can think. Triple S, sigma. The symbol, force per unit area. Intensity also has S in it. That's how you can think. Strain is basically how much is the change in the dimension. N, dimension, relative change in dimension. There is N here also, there is N here also. That's how you can remember it. Change in the dimension. Alright, it's sounding like having similar alphabets or similar sounds. That's how you can relate it. Yep. Is that clear? Everybody with me? Yep. If you get stress, will you get strain? We'll come to that. We'll just come to that. Now, just one second. Now, imagine there is some body, okay, and what happens is somebody applies some force on it, so because of which it gets deformed. So let's say there is an external force acting on it. So there is some external force acting on it, because of which there is a restoring force, and we all know that the restoring force is numerically equal to the external force. So there is change in the dimension. So if I ask you, is there stress? Is there stress? Obviously there is stress because there is force trying to change it. That force intensity is there. So yes, there is stress. Will there be strain? The answer is yes, because the dimensions have changed. This was the original. This was the natural position. This was initial position. This is natural shape and size of the body. Now this is being deformed. This has been now deformed. This has now been deformed. So now you might be thinking, maybe the stress is related to the strain. If I increase the stress, strain will increase. If I reduce the stress, strain will increase. Now tell me one thing, does stress cause the strain or does the strain cause the stress? Think about it. Think about it and tell me. Who causes whom? Who is the cause? Who is the effect? Who comes first? Because there is strain, that's why the stress happened, or because there was stress, that's why the strain happened? The answer to that, I think some of you are answering it correctly. Yup, Shri Ganeshan, correcto. The answer is the stress always causes the strain. Because there was some force, that's why it elongated, and that's why there was restoring force. So there was stress, and that's why it got elongated, means it got strained. It's not going to happen that, the body on its own got elongated. Oops, I got elongated. Hey, apply a force on me. No, you apply force, I will elongate, there will be strain. So understand, this is always the cause. This is always the cause, and this is always the effect of that cause. Now this stress and this strain are related to each other. This stress and this strain are related to each other, and you will see there is a certain thing called as an elastic limit. Within elastic limit, you will see that there is a certain relationship they obey, and that relationship is as follows. Sigma is proportional to the strain, and this is called as your Hooke's law. Hooke's law. Okay, this is called as your Hooke's law. Stress is directly proportional to the strain. That is called as your Hooke's law. So more stress will cause more strain. Less stress will cause less strain. No stress will cause no strain at all, because there is no deformation happening. And the constant of proportionality, sigma by epsilon naught, is called as the modulus, I'll call it modulus of elasticity. Modulus of elasticity. This modulus of elasticity, this particular quantity that you see over here, all right, this is completely dependent on the material. Meaning, if it is steel, this ratio is fixed. If it is aluminum, the ratio is fixed. If it is cement, the ratio is fixed. If it is rubber, it will have some another ratio. If this value of modulus is large, what does it tell you? If it is large, that means you need more stress for the same deformation. So the material is very difficult to deform. Okay, so I'll mention all the pointers on the next slide over here. So my dear warriors, modulus of elasticity. Modulus of elasticity. Modulus of elasticity depends on what and all does it depend on? It depends on the material. Strictly speaking, it also depends on the temperature. If you heat it, it might become very easy to elongate or pull it and all those things. So it slightly also depends on the temperature. Second thing which you should also know, the modulus of elasticity. The modulus of elasticity will have an unit. What is the unit of modulus of elasticity? Sigma is Newton per meter square. Epsilon has no unit at all. It has no dimension at all. So Newton per meter square upon nothing will be Newton per meter square. So that is why this also has the unit of Newton per meter square or Pascal in SI units. This is obviously in SI units, but in CGS unit you can use dyne per centimeter square, that is in CGS unit. Is that clear? Also keep this in mind. If the constant, if this modulus of elasticity is more, if it is more, then what does it tell you? It is difficult to deform it. It is very difficult to deform it. If the modulus of elasticity is less, It is very easily stretchable. I can easily elongate it or compress it because it requires less stress per unit, less stress per deformation or for that particular strain, I can say. Is this point very, very clear? Yes. So modulus of elasticity is completely a materialistic property. Usually, just to give an example of how these values of modulus of elasticity are, example, the modulus of elasticity for steel, is approximately 2 into 10 to the power 11 newtons is what you need per meter square. That's crazily high. Okay. For water, it is of the order of 10 to the power 5. The bulk modulus we'll be talking about. It is of the order of 10 to the power 5, 10 to the power 6 for water. For steel, it is 10 to the power 11. So those are the typical ranges which you should know that, yeah, it is this high. It is not going to be like 5, 6, 7, that low constant. It's a very, very high value that you generally see. Okay, great. Thank you, Levi, so much. Yes, Shri Ganeshan. Yes, aspirant, very good. Stress is an internal force. Yes, you can think of it. A lot of people do not know this. In fact, when I used to take teacher interviews also, I used to ask the teachers, is stress due to external force or internal force? Okay. And many teachers used to say, yeah, you know what, you apply the force from outside, it is the external force per unit area. No, actually not. It is the internal restoring force. It is the internal restoring. Restoring is there within the solid. But it so happens that when you stretch something, the internal force becomes equal to the external force after it achieves equilibrium, or if the acceleration is not there, velocity is not changing rapidly, if it is a slow deformation, then yes, this force and this force are numerically equal. But it has been defined for this. Imagine an example where you pull something and release it. It will take some time, right, to come back. Won't it take some time to come back? So when you release it and it is coming back, the outside force has gone, but still there is stress. Are you getting what I am saying? You pull something. There is external force, there is restoring force. You remove the external force. It will slowly come back. While it is coming back, doesn't it have stress? So how does it have stress? Because the outside force has gone. The inside force is there, that is the restoring force which is there. And for that small amount of time when it is coming back, there is stress. So stress is that internal restoring force per unit area. I hope this is very, very clear. You can ask any of your friends, and most of your friends who have not attended it properly or who do not know the concepts, they will give you a wrong answer. You try it out. Ask your colleagues, your friends, your classmates, they will definitely give you a wrong answer. Okay. So that was stress, modulus of elasticity. Now remember, there are 3 kinds of deformation that we saw. What were those 3 types? First was longitudinal. So we naturally should have longitudinal stress, longitudinal strain, longitudinal modulus of elasticity. Then we saw bulk modulus also, and then we saw also shear modulus. We saw shear deformation. So for all these 3 kinds of deformation, longitudinal, shear and bulk, each of them have their own stress, strain, modulus, which have been defined, but the formula is almost the same. Force per unit area will be the same for stress. For strain, again it will be a dimensionless quantity, and modulus will be obviously stress by strain. So let's see all of them so that the things are very, very clear in your head. So starting off with longitudinal deformation. My dear warriors. So imagine this is a rod of certain length L, okay, and now the rod changes its length to, or let's say it was L0 and now it became L, and now it has changed its length by X. So from outside there could be a force which will also be the restoring force internally, that is understood, okay. And obviously there is an surface area that will be there over here on which the force has been applied, okay. So first of all, let's define stress. Stress sigma will be the force which is acting per unit area Sometimes you can also write it as force by pi r square if it is a circular phrase. If it is not, then you can just put it as A and you can measure that area if it is a square, rectangle accordingly. Next thing is the strain. Next thing is the strain, which is epsilon naught, which is epsilon, which is the change in length upon original length. The change in the length is x. The change in the length is x. Upon original length is basically L naught. Upon original length is basically L naught. Understood, my dear warriors, still here? Very good. Very good. Awesomeness. Now, the last quantity that we'll define is the modulus of elasticity for longitudinal behavior. So, this is for longitudinal behavior. Yes. So, what is that modulus of elasticity? That symbol is Y, which is also called as Young's modulus, which is also called as Young's modulus. Young's modulus. The longitudinal modulus is also called as Young's modulus. It is this stress, which is longitudinal stress upon the longitudinal strain. Whatever stress and strain we found out over here, please remember these were both longitudinal. This was both longitudinal stress and longitudinal strain. So you divide the stress with strain, you get the Young's modulus. So that's why the Young's modulus is that force per unit area upon the change in length upon the original length. Upon the original length, let's say L naught, whatever you want to call it. So that is Young's modulus. The stress of longitudinal upon the strain of longitudinal. Till this point, is it clear, my dear students? Can we go ahead? Till this point, is it clear? Hello, Sian. Yeah. Very good. So since this is 11th moving 12th batch, I am going right from the proper scratch level 0 to hero level. So we are seeing the entire theory so that you understand the concepts behind it, right? Cool. Moving on to the next, and that is basically your longitudinal is done. So let's go to shear. Let's basically go to shear. So for shear, what we do is we show two surfaces. This is one surface here. This is another surface over here. Okay. They have an area A. Then what we do is basically we deform it in the sense those two faces would have now slid with respect to each other. Just join them like this. These two surfaces have slid with respect to each other, and there is some deformation angle wise, so I'll call it theta. There is some deformation angle wise, I'll call it theta. And on the surface, I have applied a force like this. So remember, the force is parallel here. In this case, it was perpendicular. This force was perpendicular. Here the force is parallel. Here it is parallel to that area. It's parallel to that area. So if you see this part closely, you will realize that this point has actually gone ahead by an amount x. This point which was here has now gone ahead by an amount of x. And let's say the separation between them is, let's say, L or H, whatever you want to use. So the shear stress sigma will be given by the force which is acting per unit area. Same formula, no change. The shear strain which is acting, epsilon, will be, how much is the change? X per unit separation between the layers which are sliding. The separation between the layers is L, so it will be X by L. But if you look at this small triangle, you will see it is a right angle triangle. X is opposite to theta, L is the adjacent side. So X by L, opposite by adjacent of a right angle triangle, will be tan theta. So that is why you can also write tan theta. Theta is the angular shift which is happening on the surface. Is that clear, everyone? Great. So lastly, what is the modulus of elasticity? The modulus of elasticity is called as rigidity modulus, or even shear modulus, And this rigidity or shear modulus is obviously your shear stress divided by shear strain. Shear strain. Stress by strain. Same definition is being used. The symbol here is a G, and that is obviously going to be that F, which is going to be, I'll put one more symbol over here. This is F parallel. This is F parallel. Here this was F perpendicular. It was perpendicular. That's why I'm deliberately putting F perpendicular and F parallel over here. So even in the previous slide, I can just put F perpendicular like this. So this will be F parallel per unit area divided by your tan theta. Divided by your tan theta, or just X by L also will work. So that is your shear or rigidity modulus. Till this point, everything is clear? Everybody? Okay. So you've gone right from the basics, moving on to the last one, and that is your bulk. And that is your bulk deformation. So in that, imagine a particular gas or a liquid has some volume V0, and because of the changes of pressure, what happened is the volume changed to a new volume, let's say V, to a new volume which is, let's say, V. Okay. Now, if this has to happen, should pressure increase or decrease? Think about it. If it has to expand, pressure should decrease. If it has to compress, pressure should increase. Is that right? Cool. So whatever pressure was there, has to change in some or the other way. So let's say earlier the pressure was huge. So I'll show big arrow marks over here. Big arrow marks over here. Later on, the pressure has decreased. So I'll show small arrow marks on this. I hope you see the difference. Yes, small arrow marks on this. Pressure was more, pressure has become less. So there is a change in the pressure which is happening. That change is called as the bulk stress. That change is called as the bulk stress. So bulk stress is basically the change of the pressure. Change of the pressure. Change of the pressure. So the bulk stress is technically delta P. Lot of people think it is P. No, and many students lose marks because of this. It is not the pressure which causes the change of volume. It is the change of the pressure which causes the stress or the change in the volume. Is that clear? Wow, ABD, nice to see you. You are in IIT Kharagpur. I am very good, and looks like you are having a great time. Wow, nice to see my old offline students, and you are one of those visitors who randomly ends up in the sessions and say hello. It means a lot, and I feel very happy and delighted when I see my old students. Glad you are enjoying it, I hope, and you are probably in a lot of clubs and hopefully having a gala time in the hostel, having new friends, using all the facilities whatever are there. All the best, my dear students. Yes. So bulk stress, remember, is change in pressure. So similarly you have bulk strain. Similarly you have bulk strain. Now this bulk strain will be nothing but the change in volume upon the original volume. Change in volume upon the original volume. But there is a problem. See, if delta P is positive, meaning the pressure has increased. If pressure has increased, the volume will decrease. If volume has decreased, the pressure will increase. So technically, usually these both will be of opposite signs. If delta P is positive, delta V will be negative. If delta P is negative, delta V will be positive. Did you understand why they are going to be of opposite signs? If pressure increases, volume will decrease. If pressure decreases, that means delta P is negative. Then delta V will be positive or it will be increased. So usually they are of opposite signs, and that we will take into account while defining the modulus. So the bulk modulus. So the bulk modulus means it should be actually modulus. So it should be, truly speaking, the bulk stress upon the bulk strain. But yeah, everything is with mod sign, not just here, but even over here. Okay, that is the reason why the word modulus was even introduced. So the mod sign is there, just that we do not show it, or if one is negative, one is positive, we automatically make both of them positive, or we just take the mod of it. So always that mod symbol was there. Just think of it that way. So over here, bulk modulus symbol is B, and bulk stress is delta P. Bulk strain is delta V by V. But since I always want the mod value or the positive value, you put a minus sign, because I know one of them is always positive, one of them is always negative. So to make it positive, you multiply with a negative number, so that negative into negative becomes positive. Did you understand why that minus sign came? Did you understand why that minus sign came? Everybody with me? Yep. Is it like solids? Yes, the formula is very much like solids, stress by strain, but instead of force per unit area, you use change of the pressure. That's the only difference. If you compare this slide with this slide, what's the difference? Force per unit area, force per unit area. Here we have change in the pressure. Okay, so that's why I said the behavior and the formula are looking very similar, but you will see a small subtle difference the moment you come to solids, the moment you come to liquids or gases. The moment you come to liquids or gases, looks similar but slightly different. That's all. So that is your bulk modulus. That is your bulk modulus. So these are the three major slides of this chapter. First is for longitudinal stress, strain and modulus of elasticity, called as Young's modulus. Second one is shear, this kind of sliding. So the parallel force on that area upon the strain, which is X by L. X by L comes out to be tan theta, that is G. Last is bulk modulus, change in the pressure upon relative change in volume will give you the bulk modulus, but put a minus sign because I know both of them will have one negative sign at least. So you multiply by negative to make it positive. Very good. How? Yeah, so that's why I gave this diagram. Just think of it this way. Just think of it this way. If there is a balloon like this, there is pressure acting on it. There is pressure acting on it, right? Will this pressure change the volume of the balloon? No, it will just stay there. It will be at equilibrium. It will be at equilibrium. It will stay there as it is. But if that same balloon, now you want to compress it, you will obviously apply more pressure. You will apply more pressure onto it, right? So there is some delta P. That delta P is the cause. So that is why that is the stress, not just the pressure. Is that clear now? Understood? No, John, I don't know Malayalam. Perfect. Give me a thumbs up, smash the like button already if you haven't. Let's move now. Let's move now to the next one. Ready for it? Okay, perfect. Now, some more formulas which are going to come, okay? These are all problems actually which are asked, but I'm going to make it look like theory, because the moment you see such a question, you will be just substituting, or you know what is the approach for it. One of the major things which happens, especially with regards to longitudinal stress, is you take a rod of certain length, certain area, and compare it with a spring of constant K. How do you do that, you might say? All you need to do is just imagine the rod is being pulled or stretched. So you stretch it by an amount X by applying a force of F. Same thing, this spring also gets basically elongated by an amount of X due to an application of the force F. Let's do a small comparison between the two and you will understand it for yourself what I am talking about. So over here, if I write Young's modulus, it will be stress by strain. Stress is force per unit area. Strain is the change in length upon original length. Let's rearrange it. So F A will come down. Here you have X and L will go on the top. That is Young's modulus. Rearrange it further. You will get F is equal to Y. A will go on the top. X will also go on the top. L will come down below on the other side. F is YAX by L. But for the spring, I can just say F is equal to K into X. K into X. Now comes the real comparison. Force is directly proportional to X and that constant of proportionality is K. Force is directly proportional to X. Constant of proportionality is K. Look over here. This is the constant of proportionality, you can see, and the force is again proportional to X only. So aren't these two formulas very, very similar, just that the constants have changed? So can I not say a rod which is elastic can be treated like a spring of constant YA by L, of constant YA by L? So K will be YA divided by L. So what does it mean is that an elastic rod can be treated like a spring of constant, YA by L. That is the meaning of it. Is that clear? Very, 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 very crucial. Very, very, very important formula which I have been giving you over here. That is very important. Using this, we can also find the energy stored in an elastic rod. We can also find the energy stored in an elastic rod. How do I do that? Just like how I did energy stored in a spring. The energy stored in an elastic rod can be compared to a spring. Energy stored in an elastic spring. So I can just write energy stored in an elastic body. Is like the energy stored in a spring, and the energy stored in a spring is none other than half kx square. But wait a minute, I just figured out whenever I have a rod, I can convert it into a spring of constant k, which is YA by L. So instead of k, why not write it as YA by L just from before? Just from before the last slide, I'll just write it as YA divided by L, and then I can put x square. So that is the elastic potential energy which is stored. Very important formula again. And all of this happened because I knew this particular formula. Spring constant is YA by L. So this is a very, very easy way of writing how much energy is stored in a stretched or a compressed rod or a deformed body. Is that very, very clear? Can the spring be treated like an elastic rod? Definitely, a spring can be also treated like an elastic rod, but usually would not do that because spring makes the job easier. Rod does not make it easier. You will be making it more complicated. So always make a rod into a spring, because spring is something which we commonly understand very easily. Not just this, we can do one more change to this. And you will see the formula looks even more simpler. Let me show that to you on the next slide. So the elastic potential energy, whatever I got, what if I divide it by the volume of the rod? Meaning, look at this, half YA by L x square. I'll just write it on the top. So half YA by L into x square. Okay, so this is the elastic energy divided with the volume of the rod. How much is the volume of the rod? The volume of the rod is area into length, right? So see, what do I get? I will get half, then y is there, a got cancelled, x square is there, and then I have L square. Is that right? Everybody till this point, is it clear? Okay. Now what I will do, I'll just play with this. Observe carefully. Half Young's modulus, I will write this as x by L whole square. Deliberately I wrote it. Why did I write it? Because I know x by L is change in length per unit length, original length. So that is the ratio, dimensionless ratio, strain. So can I not just write it as half Young's modulus into strain square? Half Young's modulus into strain square. Everybody with me? Pakka? Okay, but wait a minute. Young's modulus is actually stress by strain. Young's modulus is stress by strain. So into strain square. strain will cancel. I will get half stress into strain. So I got formulas from here which are dependent on stress and strain, and this is nothing but the elastic energy density. Elastic energy density, rho. Usually rho or D is the symbol for density, mass per unit volume. But this rho, I have put a word, elastic potential energy, meaning how much energy is stored per unit volume. This is half stress into strain. The unit of this will be how much joules is there per meter cube. This is your elastic energy density. Elastic energy density, because it is per unit volume. How much energy is stored? Half stress into strain. Half stress into strain. Okay. It is imaginary. What is the use? No, it's not just imaginary. It is used to understand how much energy is stored per unit volume. Certain times, if lot of energy is stored per unit volume, then it can cause certain problems. Okay, like it might probably not handle stressful situations very easily. Okay, because already lot of energy is being stored per unit volume, and everything will have its own capacity. Maybe cement has some capacity, how much energy it can store. If it breaches that point, then it might just crumble, it might just break, or it might just crack. Okay, so it tells you where can I store more energy per unit volume. Sometimes it can be used for an application. Oh, this material, this metal can store more energy per unit volume. Let's use this rod and I can stretch it and I can store it over here. Maybe in a spring or a clock. All right. So when you want to design it, or a shock absorber, right? So you want to make sure that a lot of energy gets absorbed, a lot of energy gets stored inside of it wherever there is a hump or a sudden variation in the ground surface. So many applications are there of energy density also. All right, so that was energy density, and we saw how spring can be treated like a rod, or rod can be treated like a spring. Another important variation of problem that you will see, these are all PYQ based questions, these are all PYQ models, patterns which I am explaining to you. Let me tell you that. All right, another important thing is where you change the pressure and then you find, how much is the change in the density. So this is also an important problem or a type of question. You can also look at it like a theory. So density variations due to pressure changes. How does that formula or that theory look like? Let's have a look at that as well. Okay, so let's say initially, what happens is the original density is, let's say, rho naught, and that is mass by V naught. That is original. Then final density, because of the changes of the pressure, what happens is the new density, mass won't change, just that the volume will change. So this is how it will look like initially and finally. But how are they related to the change of the pressure? Let's come to that point now. So for that, let's bring in bulk modulus. So the bulk modulus B is nothing but the change of the pressure upon, with negative sign, delta V by V. Okay, let's take V on the top for convenience sake. So minus delta P into V, but this V is the original volume, so I'll put V dot or V naught over here, and change in the volume is final minus initial, so V minus V naught. Final minus initial is delta V. If you want, we can take the minus sign also inside if you want to make it look really good. So it will be delta P into V naught, whole thing divided by V naught minus V. I just taken the minus sign inside, nothing great. Okay, now what we will do, we will take V naught, V naught, everything to the other side. Let's bring B below. So how will it look like? It will look like this: V0 minus V divided by V0 is equal to delta P by bulk modulus. Delta P by bulk modulus. V0 by V is 1, and here you will have V by V0 is equal to delta P by bulk modulus. Now what we'll do, take this guy over here, take this people over here, so it will become 1 minus delta P by bulk modulus is V divided by V0. Now what will be V divided by V0? You can get an idea right from over here. Check this out. From this you can clearly see V0 is equal to M by rho naught, and from this you can see V is nothing but M by rho. So when I divide V with V0, this guy with this guy, M will get cancelled, M will get cancelled. So think about it, what will happen? V will be nothing but M by rho, and V0 will be nothing but M by rho naught. M will get cancelled. It will just become rho naught by rho. It will just become rho naught by rho. Perfect. So just have to rearrange now. So take rho on the upper side and take these people on the bottom side. So rho will be rho naught 1 by 1 minus delta P by your bulk modulus. So that becomes your formula for finding the density with pressure changes. You put up the pressure change, divide it with the bulk modulus, 1 minus that will give you the new density if you know the old density. Understood? Vanakkam Sujit, thank you for all the love from Tamil Nadu. Yeah. The E is x by L only for shear stress, but we are using longitudinal. How could it be possible? It's just a formula. It's just a symbol, Ganeshan. So over longitudinal, x means elongation. In shear, the x means sliding of the surface. How much was it? In longitudinal, L was the length. In shear, L was referring to the difference between the layers, the separation between the layers. So symbol can be same, right? You can use D for density, you can use D for distance also, right? So same way, you can use S for maybe surface tension, you can also use S for displacement. So don't get confused by the symbol, the meaning is very important. That's why whenever I explain any formula or write any formula, I don't stress so much on the symbols. Symbols can be different in different books. What is important is you understand how it is being said or what is the meaning of it. That's why we always say stress is the force which is perpendicular to the surface. Longitudinal one is force which is perpendicular to the surface upon the area. That's how you should actually remember the formulas. Don't remember it by symbols. Remember it by what it means, what it exactly says. Okay, cool. Then another kind of question that you might get. Another kind of question. Again, these are all very important previously repeated patterns, previously repeated asked questions, either formula wise or just pure substitution wise, or maybe there was a mixture of 2-3 concepts, but these are most important concepts. Is where there is a rod and it is hanging, and because of its own weight, and then you have to find how much is the total elongation in it. This is also a very, very commonly asked question. So there is the length of the rod given. There is the length of the rod given. The area of the rod is given. The density of the rod is given. Young's modulus is given. So elongation due to its own weight. Very commonly asked previous year question. Very commonly asked. This year also it was asked in 2024. So I'm guessing for 2025 also it might be asked again. Elongation due to its own weight. So what happens is this rod will experience some stress because of its own weight. It will elongate, and the problem in this question is that the value of the stress is not uniformly distributed throughout the rod. Each and every point has a different value of the stress, and that's what creates the issue, or that's what is the catch in this particular problem. So let's understand why this happens. Say for example, there is one pandu which is hanging from a branch of a tree, and then there is another pandu holding his legs and hanging below him. There is another Pandu holding his legs and hanging below him. And then there is another Pandu holding his legs and hanging below him. If I ask you whose hands will be highly stressed, whose hands will be under high tension, will it be Pandu number 1 or will it be Pandu number 2 or will it be Pandu number 3 or will it be Pandu number 4? They are all holding each other and hanging from the branch. Quickly answer it. Quickly answer it in the chat box. Come on, my dear warriors. Who do you think will be more stressed? Will it be the uppermost or will it be the lowermost? Think about it. The uppermost is not only holding himself but all the people below him. The lowermost is just holding on to this person. There is nothing for him to pull. So this Pandu is relatively less tensed, less stressed. Pandu number 1 has the highest tension. So high forces over here and there are low forces, low stresses over here. So as you go on the top, you will see the stresses will increase, the tension will increase. Is this point clear? Very good. Yes. Yes. Very good. Manikandandan, my God, I left 2024. Who said that? And you made that decision just because I take one class of 2025. Very good. Thanks. I now got to know how much you trust your teachers, how much you believe in your teachers. Very good. Congratulations. If you want to believe that, please believe it. Okay. So now over here, that you understand that uppermost point will have to hold the or support the entire weight which is hanging below. The same thing is also applicable for a rod. The same thing is also applicable for a rod or a string which is heavy. Think about it. If I take a point here, let's say it is at a distance of x, the tension that it experiences will vary as I go from bottom to the top. Here it will be negligible. As I go on the top, tension will be maximum. So this will be the point where max tension will be there. This will be the point where minimum value of the tension will be there. How much is the tension at any random point can be easily found, because the tension will only have to support this much mass, weight. So the mass of this part, will be the total mass, per unit length. The total mass might be m. So how much mass is there per meter, per unit length, and you just multiply it with x. That is the mass of only this much part. Is that clear? Is that much part clear? How much kg is there per meter into the meters will give me how much kg is left over here. Is that clear? Very good. Yes, my dear Manikandana, I will be taking classes for you too. It's just that maths CBSE board exam is going on, right? So we are also simultaneously going to launch an amazing module 2 for all of you for the second attempt. Don't worry. Okay, so there is an amazing plan. 2-week challenge is what is going to come up for all of you, and we will try to get you 99 percentile in those 2 weeks. So there is a lot of work which is going on at the back. I'll be announcing the plan by Saturday, maximum Sunday. That's when your maths paper will be over. All right, so hold on, stay tuned and get your friends too. Okay, so if this is the case, what will be the tension, my dear warriors? What will be the tension, my dear warriors? It will be the weight hanging below. It is the weight which is hanging below, right? It is the weight which is hanging below. What is the weight? Mass into gravity. Mass is m by L into x, the whole thing into g. So that is the tension. So basically the tension is mg x divided by L. So as x changes, tension also changes. If x is 0, tension is 0, minimum tension. If x is L, then tension is maximum. Okay, it will have to support the entire weight of the rod. Till this point, if it is clear, then we can also figure out how much is the stress which is developed here. The stress which is developed at any point, sigma, will be tension by area. So it will be mg x by L into A. mg x by L into A per unit area. So the stress is also changing. So the elongation, strain will also be different. This part will have different strain, this will have different, this will have different. So because the strains are different, the total elongation will be the sum of all the small changes. Will be the sum of all the small changes throughout the rod. That means I need to involve integration or derivatives. Is that very clear? Yep. Yes. So let's try to relate that as well. Till this point, we have just realized that the stress is dependent at which point you are calculating it. By the way, we can also do one small magical thing over here. Mass is nothing but density into volume. Volume is basically LA. Volume is nothing but LA, and Gx divided by this LA is as it is. LA, Los Angeles got cancelled. So it will become rho Gx is the stress. Rho Gx is the stress at any given point. Cool. Now, since the stress is different, observe how I am looking at this particular problem. Here, the stress is less. Here, the stress is slightly more. Here, as you go, the stress is even higher. So, if you probably take a slice of the rod here versus here, okay, if I take the same slice of the rod at 3 different locations, here the change in length might be negligible or small. Here the change in length might be slightly more. Here the change in length might be even more because the stress is more. So the change in the length is different at all the points. Here it is something, here it is something, here it is something. Maybe it is dx1 here, or I can call it delta 1 here, delta 2 here, delta 3 here. So can I say that the total elongation is nothing but the sum of all the small elongations which are going to happen, all the sum of the small elongations that are going to happen at each and every point. That means I need to involve integration. Understood, my dear warriors? So that is how critical, how important this problem is. So let's take an element and let's figure out what and all things need to be drawn in that particular small element. So I will take an element which is at a distance of x, having an original width or length of dx, having an original width or height or length of dx. X is from the bottom. Remember, this is the bottom. Just same bottom like we took it over here. At x, I've taken a small element, a small piece of that rod, okay, and that rod element will elongate by d small l. D small is the small elongation, that happens in that particular rod. And at that point, I know there is tension. And that tension, we figured it out right over here, was rho gx, was nothing but rho g and x. Perfect. Now what do we do? Let's use our Young's modulus definition and see what do we exactly get. By Young's modulus definition, it is nothing but the stress by the strain. The stress, oh sorry, this was not tension, this was stress. I'm so sorry. This was stress. Stress was rho gx. Yeah, stress was rho gx. Stress, I already figured it out to be rho g and x. That is done and dusted. The problem is, what about the strain? Strain is how much did it change by? That was nothing but dl upon the original length, that was dx. Original length was basically dx. Did you understand it? How we got it? Original length was dx for that element, and the change in that was dl. Let's play around with this. Let's rearrange it. It will look like this. dl, I will take it on the top. Rho is as it is, g is also as it is, x is also as it is. Dx, I can bring it on the top, and y I can bring it below over here like this. So dl will be rho g by y x dx. Clearly it is in the integrable form. So if I integrate small dl and bring rho g and y outside the integration, I'll just have integration of x dx. So what are the limits of the integration is very important. See, this will go from 0 to the complete length. 0 till the complete length of the wire. X is this x, remember that. X is this x. So it will start from 0, it will go till this. But do not say dl will also go from 0 to L. This will go from 0 to the complete change of the length. This is the total change of that length which we are talking about, total elongation. So that total elongation which is there is the sum of all the small elongations. That means it is integral of dl. It is integral of dl from 0 to whatever delta L we are talking about. That is what it is. So just put delta L over there and we'll get the answer. So this will be delta L will be rho g by y, and this will be nothing but L square by 2. So that is the final answer. Rho g L square by 2y. Rho g L square by 2y. Is that clear? Shri Ganeshan, that's why you should see teachers solving problems. Teacher solving even complex problem is fine. Even if you don't understand, sir, you thought so much, I will never think, sir. Don't say that. In fact, that is the reason why you're watching it, because you don't know how to think right now. You're watching the teacher and then you will try on your own with simple problems, and over a period of weeks, not 1 day, 2 days. If some teacher tells you, no, on YouTube or anywhere, I will teach you concept and within 1 day you will understand everything. Not possible. You have to practice. You have to make an effort to slowly scale up your level. That's when you reach that level to understand and solve even difficult problems. Is this point clear, my dear students? Vakka, done and dusted. Shall we go ahead? Shall we go ahead? Okay. Then another type of question which often comes. Okay, let's have a look at that as well. This is also very, very important. This clears the problem between shear and longitudinal stress, and not many people know this. Imagine that there is a block and you have pulled it by some force like this. You have pulled it with some force like this, and somebody gives you a cross section in this particular manner, and let's say this particular angle is A. This particular, sorry, not angle is not A, angle is, let's say, theta. This particular angle is theta, and this inclined area is A. The inclined area is A. It could be different from this area also. This actual area will be different from this. You have to visualize it a little bit, maybe like this, maybe it is like this. Just visualize it. This is here, right? Okay. Something like this. Are you able to visualize it now? How this area is? Question is, yeah, if this particular thing has already been given to you as A, question is find the shear and the longitudinal stress. Find the longitudinal and the shear stress on that particular area. That is what the question says. Let's try to understand, why there will be longitudinal as well as shear stress, and that will only come to us by drawing the free body diagram. What I will do is I will only take either this part or that part. I will not take both the parts. Take either this part or that part. So let's say I take this part. So if you take only that part of the diagram, it will look something like this. It will look something like this. And then you have this particular area over here. You have this particular area over here, something like this. Okay. Now, if there is a force acting here, because this body is in equilibrium, shouldn't there be an equal and opposite force to keep it at rest by Newton's first law? So 100% there will be a force which is internal on this section. Basically, if you take any section of that rod, there will be force, or else the rod will completely break. If there is no force, then this force will just take away this part of the rod, and that force will take away that part of the rod. So 100% there will be a force over here. Okay. Now it is clearly mentioned this angle is theta, or basically even this angle will be theta, or even this angle will be theta. That is already given to you. Maybe I can split the force into two components. One component like this and the one component like this. This component is perpendicular to the surface. This component is parallel to the surface. Now you have two components, and now probably you might be understanding why there is longitudinal and shear stress. This part is perpendicular to the surface. That's why it's responsible for longitudinal behavior, longitudinal deformation. This force is parallel to the surface. That's why it is responsible for shear behavior, shear deformation. Is that clear? Perfect. So how much are these values? So if this is theta, think about it. Even this will be theta, by the way. If this is theta, parallel lines, so same angle, so even this will be theta. So naturally this parallel will be cos component, so it will be f cos theta, and this will be f sin theta, f sin theta. Is that clear? Everybody with me? This will be f sin theta. Very good. Now what do? Just write down the stress and the strain values, stress values for both the things. So longitudinal stress will be always f perpendicular by area. F perpendicular is just f sin theta, and the area which was given to me already was A, so it is f sin theta by A. The shear stress will be f parallel by the area, so f parallel was f cos theta divided by A. That's it. That's how you find the shear and the longitudinal stress. Is that clear? Did you love these questions? We are doing lots and lots of questions and their varieties. These were asked directly or indirectly in your previous year JEE papers. Let me tell you that. Yes, these are all important concepts, important derivations, important formulas, important question types, important pattern types. Now comes the next part of this chapter, where we discuss a graph, a very important graph, which relates the stress and the strain. Very, very important, very, very crucial. So let's draw it first. Okay. So here we will have strain. Here we'll have stress. Actually, let's have strain only. Strain, which is epsilon, and here we'll have stress. Okay. Stress versus the strain graph starting from origin. How would this graph look like? In fact, just some time back I told you about Hooke's law, right over here. Where did it go? Modulus of elasticity, Hooke's law. Stress is proportional to strain. So you'll be like, sir, it is proportional, so 100% it will be a straight line. And you are partially correct if you think like that. So let's draw the graph right over here. So using Hooke's law, one can easily say that, listen, you will see that the stress is directly proportional to the strain. So it will be a straight line, just like this. But it will not remain straight line forever. It will start becoming curved, non-linear, basically, after a point. So there is a point till which it remains a straight line, and after that it is not proportional. So first of all, I'll label that point over here. Label that point over here as P, and after that it is going to be non-linear in nature. or sometimes I can just call it as point number A, and it is going to be non-linear like this. This point A is basically called as the proportional limit. This is the only point till which the stress is proportional to the strain. Basically, Hooke's law is valid in this particular zone. Is that very, very clear, everybody? Very good. Also, if I am increasing the stress, the strain increases. That means I am pulling it more, it elongates more. If I leave it, then it will come back. So I will also put an arrow mark over here. That arrow mark shows what am I trying to do. Here I am increasing the stress, so the strain also increases. This part represents strain and stress, both are reducing. So it again comes back to the original point O. What happens after A is a non-linear behavior, but this double arrow mark still persists. Meaning, if I increase the stress, strain increases. If I release the stress, the strain reduces and comes back to the origin. So it's a two-way path. It's a two-way, like you have one-way road and two-way road, everybody. When you're traveling inside the city, one ways and two ways, same way. So this is a two-way path. So this remains non-linear till a certain point, and that certain point I will call it as B. Now what is this point B? This point B is basically called as the elastic limit. Elastic limit. In fact, the region from your O then to A to B, this entire region is basically called as the elastic zone. Elastic zone. Why elastic zone? Because elasticity means when you release it, it comes back. It regains. It's a temporary deformation. It's not permanent. So if it is coming back, it has to be elastic in nature. Only difference is from A to B, it is not proportional, it is non-linear. It could be some x square, x cube, some equation is there, but it is not directly proportional. It's not a straight line. The stress that you get at point B, okay, the stress that you get at particular point B, the stress that you get at that particular point B is also called as yield stress. Yield stress. Why this yield stress is a particular importance is because when you are designing a table, machine, car, aeroplane, rocket, anything, fan, any holder, any building, bridge, doesn't matter. Yield stress tells you this is the stress till which the material can handle it properly without getting permanently deformed. If you apply little bit more stress, it will be permanently deformed then. So ensure that your values of the forces and the stresses are within the yield stress. I'm not saying it's going to break. No, it's not going to break. It's just going to be permanently deformed. Like, for example, you might have experienced this with spoon. You bend the spoon, leave it, it comes back. Bend the spoon or a scale, leave it, it comes back. But if you apply too much force, it might not break, but it will get permanently, that bend is there. Have you experienced this? Maybe you would have got beating also, that why are you bending spoons, why are you bending scales, etc. Is that clear, Niku? It's okay, you can watch the replay of the class also later on. Yep. So if you are starting your preparation today, I would say prepare at least starting from 3 hours, increase it to 5 hours. Start with 3, increase it to 5 on a daily basis. So by the time you reach 2025, you would see that you would have covered most of it. It starts with a small dx. Only when you integrate dx, you will get x. So you have to start with small amounts and slowly you have to buckle up. Don't get scared looking at the portion ahead or what is left behind. Okay, just start today with 3 hours, increase it to 5 hours. After B comes a zone where if you increase the stress, the strain increases. But if you remove the stress, then it does not come back to its original shape and size, it comes back over here. You will see that, let's say I call this point P, it has been deformed permanently because there is strain even when there is no stress. This is often called as permanent set or permanent deformation. Permanent set or permanent deformation, you can see there is no force from outside because stress gone, but strain is there. That means elongation or deformation is there. So it has been permanently deformed. Is that clear? This happens here. You can increase the stress further and you can release it. You will see it will get set at some other location. So more you bend, more you deform and release it, it will be deformed even more. So that is the reason why this zone is also called as the plastic zone, and this plastic zone continues till a point C. So this point from B to C, this point from B to C, B to C is called as the plastic zone. Plastic zone. What happens at C is it breaks. At point C, it basically breaks. In fact, the value of stress, that you get over here, sigma breaking, this is called as the breaking stress. After this, it is not permanently going to be deformed. In fact, it is going to break. So there is a breaking stress point right over here. So after this, it basically breaks. And in fact, you might even see that the graph may not even go up, it might just go down. That is very strange because the material is elongating even though the stress is reducing, because now the material has been elongated so much that the points of contact are slowly going away, the bonds are being broken, so hardly any forces are able to pull it back. So it's like it stretched so much, it finally gives up, everything rips apart, so the forces are vanishing. And it vanishes and it breaks. After this, the graph is, what just happened? Yeah, after this, basically the graph suddenly, goes down. The graph suddenly will go down. Is that clear? Yes. Very good. Sir, I finished all my 12th standard chapters by you, but I can't find EM waves. When will it be? Vidyashri, I will be taking up EM waves shortly, don't worry. But I had done EM waves in the previous years. So if you can find the older classes also, that is also fine. Is that okay? Cool. What just happened? Oh my God, don't tell me all my notes went off. It's not even hot, but why did this happen? Okay, just hold on guys. I'm just starting the computer. Looks like all my notes are gone. Oh, thank God. Please, can you open this somehow? Thank God. Okay. Luckily, my notes got preserved, or else I would have felt really, really bad. Yeah. So after this, it breaks, and you will see it basically fractures. At point F, it basically fractures. So this is the stress versus strain graph, which is very, very important, which is very, very crucial. Is this clear, my dear warriors? Yeah, 2024 student also can watch this because it is a proper detailed class right from zero to hero. I have covered all the concepts over here and I have explained the major problem types which are being asked. Now, in this particular stress versus strain graph, there is one important thing which you should probably realize. This is strain. This is basically stress. So imagine this, as I'm going up, increasing the stress and increasing the strain. At any point, if you ask me what is the height and what is the base of this particular triangle, the base will be strain, the height will be stress. So if I end up measuring the area of this particular graph under it, that particular area under the stress versus the strain graph in this case will be nothing but half stress into strain, half base into height, right? And what is this? We already know what is this particular value. We have done this right over here. Half stress into strain is the elastic energy density, joules which are stored per meter cube. So that's all. I can just say this is nothing but elastic. This is nothing but elastic potential energy. That's it. So that is nothing but the elastic potential energy. So area under stress versus strain gives you the energy which is stored per unit volume. And we can use this for another calculation also. Say for example, this is stress versus strain graph. Maybe it is straight line over here, then it is non-linear over here, then it entered into the plastic zone over here, okay? And then when you release it, what happens is it probably comes back and gets set over here permanently. Now imagine till this point, if you calculate the entire area over here, that will give you the energy which is stored till this point. But when you are removing the stress, this energy will give you the energy which has been given back to the surroundings. So if I happen to measure only this much area, what will be the area enclosed? What will be the area which is enclosed, in a loading to unloading cycle? Give me, because I have loaded it and then I have unloaded it. Remember, I have increased the stress, and then relieved the stress. I have loaded it and unloaded it. So what is that area going to give me? This is the energy stored and then energy given back. So this is the energy which is lost. This is going to always give me the energy lost as heat. It is not given back to the original source. It has been permanently lost as heat, sound, light, whatever. It has been lost. Is that clear? So this is also very important. And you know where this is important? There was a question in JEE where there were two graphs given of stress versus strain. And one of the graph, let's say this was of type A, this was of type B. One of the graph looked like this for loading and then unloading. It looked like this. The other graph looked like this, then like this. Okay, so these are the two graphs given, and they asked you if there are two types of rubbers, rubber A having this graph, rubber B having this graph, which rubber will you use for tires of a vehicle? For making the tires of a vehicle, which rubber will you use? Now you should understand, a rubber undergoes lot of stresses and strains because there is loading, unloading. The rubber will get pressed, again compressed, again relieving the compression. So there is lot of variations which happen. So loading, unloading happens continuously. If this is the graph, the area under it is less. If this is the graph, the area enclosed by it is more. So more area enclosed means more energy is lost as heat, etc. So who will get heated up fast? This will get heated up fast. Understand that. This area is higher, so area is more. Because the area is more, what will happen? This will get heated very fast. So lot of energy is lost mainly as heat. Whereas in this situation, the area is small. So less energy is lost. So that is why you will use this type of rubber to build tires. You are going to use this kind of rubber of type A with a smaller area. Is that very, very clear? But this rubber can be used for shock absorbers. For shock absorbers, you would want more energy to be absorbed. So that is why if the question said what is the rubber type you will use for building shock absorbers, you will use this quality of rubber. Is this very, very clear, my dear warriors? So this kind of questions have also come on the stress versus strain graph. One last thing over here, as you are calculating the area under the stress versus strain graph and all these things, if by chance I happen to measure the stress and strain and divide the stress with the strain, what I will get is also the slope of the stress versus strain graph, and sigma by epsilon is nothing but the modulus, Young's modulus, right? So Young's modulus is also the slope of the graph. So you can see the slope is constant, that means modulus is constant here, then modulus changes because it becomes non-linear. So modulus is only for Hooke's law where stress is proportional to strain, otherwise the modulus will keep on changing. After this though, it has become plastic. It is not going to behave only elastic in nature. So there is no point only defining modulus of elasticity over here because it has gone into the plastic zone from B to C. Is this clear? Okay, so Young's modulus is also the slope of the stress versus strain graph. You should also know this particular thing. The area under the stress versus strain graph is the energy density, not energy, it is the energy per unit volume. Also, you should know the energy which is lost as heat, etc., is the area which is enclosed in the loading and the unloading cycle. Now, as homework, I have kept some questions. You will be getting these questions as your assignment. You can call it as your practice problems. I have kept few practice problems for all of you, which are very, 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 very straightforward, especially after solving these questions, which I have done in the class. So make sure you solve it. And where do you get these PDFs? You will get these PDFs in our Telegram channel. The entire handwritten notes, whatever I just did, including the questions, everything in the Telegram, all the updates you will get in the Telegram. So make sure you have joined the Telegram channel as soon as possible. Don't think it is just any other Telegram channel. Only academic content, only the things which are relevant to you are given on this channel. Link is there in the description box. Okay, so I hope you enjoyed. You learned a lot through this particular lesson over here, which was meant to cover your backlogs. At least now you have got that confidence that yes, solids and elasticity is not that difficult looking, actually speaking. And this is what is there in the current syllabus. There were few things here and there which were sometimes added and deleted, etc. So those things we are not covered because we are just focused on the current reduced syllabus. Okay, so I hope you enjoyed it. I hope you loved this session. God bless you all. See you in the next session as well. Bye bye. Captain Shreyas signing off. Hasta la vista. See you in the comments as well.